Right. Hello everyone. I hope you guys are doing good. So today I'll be discussing the solutions to Codeforces Hello 2022, and this round was held yesterday. Before starting with the solutions, let's talk about the round. Well, I think the round was really good. It was a well balanced round. As you can see, the difficulty rise was quite gradual, although there is a somewhat big difficulty jump between A and B, as it is evident from the number of solves, but I think it's not that bad. And also, it was a very ideal div 1 plus div 2 round in a sense that any div 2 participant can at least understand the solutions to the first 4 problems uh, if he hasn't solved it in the contest. Like, they are at least understandable to everyone who is in div 2 only, right? So in that sense, it was a really good and well balanced round, I would say. I'll be discussing the solutions to the first 4 problems here. So yeah, without any further ado, let's start with the solution to problem A. Okay, so this is called stable arrangement of rooks. Let's see what this problem has to say. So we have an n cross n chessboard and k rooks, right? Rows of this chessboard are numbered from 1 to n, columns are numbered from 1 to n, from left to right and from top to bottom respectively. The arrangement of rooks on this board is called good if no rook is beaten by another rook. Like a rook is a piece which can move towards any row or any column. Like it can move to any row which is in the same row as it is currently, or it can move to any column which is in the same row as it is currently, right? So it can move right, left, up, down, anywhere it wants. And yeah, so a stable arrangement of rooks is an arrangement in which no two rooks beat each other, right? So that's a good arrangement. But a stable arrangement of a good arrangement of rooks is one in which like you can't do any moves so that one rook will beat another move, right? So a good arrangement of rooks on this board is called not stable if it is possible to move one rook to the adjacent cell so that the arrangement becomes not good. Otherwise, the good arrangement is stable. So the adjacent cells are obviously the cells which share a side. So basically, we need to find a good arrangement of k rooks on these n cross n chessboard. We'll be provided with k and n in the problem. As you can see, the constraints are really small here, although it doesn't matter. So just to reiterate, a good arrangement is one in which I have placed k rooks on the chessboard and no one attacks each other. And a stable arrangement of a good arrangement is a good arrangement in which there is no rook which I will just move just one row or one column. That is, I will move to an adjacent row or an adjacent column and it will attack another rook. There is no such rook, right? So even if I choose any out of the k rooks and move it to its adjacent cell in the row or column wise, then it won't attack any other rook. That's called a stable arrangement. Yeah, so essentially I've been given n and k and I need to find the stable arrangement of the rooks. So first of all, let's see what's happening here. So the thing is that, so once I place a rook in a particular cell, let's say I place a rook in the cell number R and column number C, then that particular row and that particular column gets blocked. So once I place a rook in the cell R comma C, then row R and column C get blocked. So that's the first thing. Essentially, I have n rows and n columns, and once I place a rook, every row, exactly one row and exactly one column get blocked, right? So this is the first observation. If I need a good arrangement, then number of rooks, that is k, should be less than equals to n. And the reason for that is that in every move, exactly one row and exactly one column are getting blocked, right? So I have n rows and n columns. So if I have more than n rooks, then I will block more than n rows which I don't have. So yeah, if I need a good arrangement, then the number of rooks k should be less than equal to n. But what about a stable arrangement, right? So in a stable arrangement, the thing is that if I have two adjacent rows, two consecutive rows that have a rook, then that good arrangement is unstable. Similarly, if I have any two adjacent columns, any two consecutive columns which have a rook, then that particular arrangement becomes unstable, right? So if I have two consecutive rows / columns which have a rook, then the arrangement becomes unstable, right? So yeah, that is it. If I have two consecutive rows which have a rook, then the arrangement becomes unstable. Similarly, if I have two consecutive columns which have a rook, then the arrangement becomes unstable. So in a sense, if I have two consecutive rows, then I can have just one row containing a rook. Similarly, if I have two consecutive columns, I can have at max one column containing a rook. And so if I have n rows, then I can have at most the ceiling of n by 2 rows containing a rook, right? Similarly, I have n columns, so I can have at most the ceiling of n by 2 columns containing a rook. So I can have at most ceiling of n over 2 rows and columns which have a rook. And once I place a rook, I am basically just occupying one row and one column, and I can occupy at most n by 2 rows and at most n by 2 columns. And so if my k is greater than n by 2, then straight away my answer is going to be no. So if k is greater than ceiling of n by 2, then answer is going to be -1. And I have already proved this because if I put any rook, I am occupying exactly one row and exactly one column, and I can occupy at max ceiling of n by 2 rows and at max ceiling of n by 2 columns. So that number can't exceed the ceiling of n by 2 ever. And so the number of rooks can never exceed ceiling of n by 2 if I want a stable arrangement. So for a stable arrangement, if k is greater than ceiling of n by 2, answer is -1. Otherwise, there is a pretty simple solution. I can start with the first row and first column and keep incrementing my row and column by 2. That is, currently I am on 1 1, and then I go to 3 3, then I go to 5 5, so on and so forth. By doing this, I am occupying every one in every 2 rows, and I am occupying every one row in 2 rows and every one column in 2 columns, and that way I am occupying at most ceiling of n by 2 rows and at most ceiling of n by 2 columns. So that is a very simple constructive solution that I have once I have proved that the answer is going to be -1 if k is greater than ceiling of n by 2, right? So yeah, that's the solution. Let's just have a look at the code for better clarity. So yeah, first of all, if k is greater than n plus 1 by 2, then the answer is going to be -1. Otherwise, initially I am on 1 comma 1 and cur is equals to 1, and then I place a rook on cur comma cur, and then I increment cur by 2. So in a sense, I am placing my rook on 1 comma 1, and then I am moving to 3 comma 3, because since I have already placed my rook on 1 comma 1, the second row gets blocked and the second column gets blocked. So I straight away move to the third row and third column and put a rook there. And I keep doing it until and unless I exceed the value k. And once I'm done, I have my valid answer, right? So yeah, this is the solution to problem A completed. It was not that difficult, but yeah, it took some time to explain it. Anyways, let's move to the second problem, problem B. Okay, so let's see what this has to say. So the integer shop sells n segments. The ith of them contains all integers from Li to Ri and costs Ci coins. So basically we have n segments with us. Every segment has 3 parts to it, a starting point, an ending point, and a cost, Li, Ri, Ci. And we have Vasya, who is going into the shop and buying some segments there, and he will get all integers that appear in at least one of the bought segments. So it's a pretty obvious thing what they're trying to say. If I am buying a segment, then basically I'm getting every integer which is present in that segment, from Li to Ri inclusive. And the total cost of purchase is the sum of costs of all the segments in it. Again, a very obvious thing. So after shopping, Vasya will get some more integers as a gift. That's the tricky part of the problem. So he will get an integer x as a gift if and only if all of the following conditions are satisfied. If he already hasn't brought the number x, and if he has brought any number L which is strictly less than x, and he has brought any number R which is strictly greater than x, right? So if for any x he has brought a number which is less than x, and he has brought a number which is greater than x, then he will straight away get x. That's the thing here, right? So yeah, we can see in this problem, we can see in this example, like if he buys a segment 2,4 for 20 coins and 7,8 for 22 coins, then in total he is spending 42 coins, and he is getting 2, 3, 4 from the first segment and 7 and 8 from the second segment. But what we realize is that he also gets 5 and 6 as a gift. Why? Because for 5 he has brought 2 which is less than 5 and 7 which is greater than 5, and similarly for 6 he has brought 2 which is less than 6 and 8 which is greater than 6. So he is getting 5 and 6 as a gift, right? So due to technical issues, only the first S segments will be available when Vasya will go, and basically Vasya wants to get as many integers as possible. That is his first priority, and if he can do that in different ways, then he selects the cheapest one out of them. So the first priority is to maximize the total number of integers that he is getting, and the second priority is to minimize the cost, right? So for each value of S from 1 to n, we need to find out total how many coins will Vasya spend, that is what will be the minimum cost if and only if the first S segments will be available, right? Not the minimum cost but the ideal cost which he will spend. So for each S from 1 to n, we need to figure out what will be the total cost if only the first S segments out of the n segments are available. That's it. Okay. So yeah, I hope the problem statement is clear enough. Let's now start making observations. So let's try to decode what this gift structure is actually doing. So what this gift thing is actually doing, right? So for any integer x, if we have a number L which is smaller than x, and if we have a number R which is greater than x, by having I mean we are buying a number L which is less than x and a number R which is greater than x, then we are simply getting x, right? So doesn't it mean that we only need to look at the minimum number which we are buying and the maximum number which we are buying, right? That's the main observation, because between the minimum and maximum, any x I choose, I will have a number which is smaller than x and I will have a number which is greater than x, right? And so that guarantees that I will get that number, right? So the only two, the first and most important observation in this problem is that the only two important numbers are the minimum and maximum integers that we are buying. Why? Because any x which lies between the minimum and for any x which lies between the minimum and maximum, I have a number which is smaller than x, which is the minimum, and I have a number which is greater than x, which is a maximum. So if I have already bought x, then that's well and good. But if I haven't bought x, then I will be surely be getting gifted x, right? Because x will satisfy all of these three conditions. I have a number L which is the minimum, which is smaller than x, and I have a number R which is the maximum, which is the greater than x, right? So the only important numbers are the minimum and the maximum integers that we are buying, right? And so what we can do is we can basically maintain the minimum and maximum integers that we are buying, and the minimum integer which we are buying will be will simply be out of the first S segment, the segment which has the smallest L value, right? The smallest L value will be the minimum integer that we are buying, and the smallest and the greatest R value will be the maximum integer that we are buying, right? So the minimum integer that we are buying will be the smallest L value. Let's call it min L, and the maximum integer that we are buying is the largest R value. So let's call it max R. And I've already proved that these are the only two values which are relevant, because I will surely get all the integers which lie in the range from min L to max R, and I won't get any other integer. That is also one thing for sure, right? Okay, great. So as you can see, the first priority of Vasya is to maximize the number of integers that he is getting, and so without even looking at the cost, I will have to buy the segment which contains min L as its L value and a segment which contains max R as its R value. And now is the question to minimize the cost. The first priority is to maximize the total number of integers that we are getting, and we will do that by buying one segment which has minimum L and one segment which has maximum R. And now we have to minimize our cost. So another observation is that we don't need to buy more than two segments ever, right? I have already proved this fact, because there will be just at most one segment which has, like, there will be one segment which has min L value as its L of I, and we will have one segment which has its R value as max R, and we can just buy these two segments if they are not the same segment. So if they are the same segment, then we are just buying one segment, and if they are different segments, then we are buying two segments. But we never need to buy more than two segments, because once we have bought a segment whose L is equals to min L, and once we have bought a segment whose R is equals to max R, we will automatically be getting all the integers from L to R, and so we don't need to buy any other segment, right? So we won't need to buy more than two segments ever. That's the first and most important observation here. Okay, so basically there are just two cases. Case 1, we are buying two separate segments. So we are buying two unique segments. And case 2 is that we are buying one segment which has L is equals to min L and R is equals to max R, right? And we can just look at both these cases separately and take the minimum out of them, right? So that's it. That is it. Basically, that's it. So now the question comes, how do we actually implement this solution? Well, implementing is a bit tricky here. So we have to use some intensive C++ STL to solve this problem. And let's discuss that. So when we are buying two unique segments, how can we figure out what will be the total cost? So for each value of L, what we can do is we can maintain a map. That map of L will store for each segment which has L of I is equals to L, the minimum cost, right? So what I can do is I can keep a map called min cost L, where min cost L of I will store the minimum cost of a segment which has L is equals to I, right? So this way I can store min cost L is equals to I as the minimum cost of any segment which has L is equals to I. And also I can do something very similar for L. So I can keep min cost L as a map, where I can keep min cost R as a map, where min cost R of I will store the minimum cost of a segment which has R is equals to I, right? And essentially the cost, if I'm taking two unique segments and I have this value min L and max R maintained with me, then the cost that I will incur is nothing but min cost L of min L plus min cost R of max R, right? So this is the cost if I'm buying two unique segments. But what if I'm just buying one segment and there exists a segment which has L is equals to min L and R is equals to max R? In that case, what I can do is I can keep a map from pair to long, or from pair to int, something like that, called both min, something like this, right? So both min of I comma j will store the minimum cost of a segment which has L equals to I and R is equals to j. And to calculate the total cost that I will incur, I will simply call both min of min L comma max R, right? So if there exists a segment which has L is equals to min L and R is equals to max R, then it will be present in our map, and we will just have this value min L comma max R of both min, and that will give us our answer. So I will take both of these costs, and the answer will just be the minimum of both of these costs. And I can keep maintaining these maps for all the values of S from 1 to n and just keep getting my answers in logarithmic time, right? I can also use unordered maps for this. That will bring down the complexity to O of n, but it doesn't really matter. So yeah, this basically completes the solution. Let's have a look at the code now. So the code is pretty short. So what I'm doing here is I am initially keeping all these three maps, all L, all R, and both. All L is just the minimum cost L, all R is just the minimum cost R, and both is the minimum cost of a pair, right? And I'm also maintaining minimum L and maximum R. Initially minimum L is infinity, maximum R is -1. As I keep going, I will keep updating these values. So I go from 1 to n, and first of all I'm updating minimum L and maximum R. Minimum L is minimum of minimum L and L of I, and maximum R is the maximum of maximum R and R of I. And then what happens is that if I don't have L of I right now in my L map, then I will make all L of Li as infinity. Similarly, if I don't have R of I in my R map, I will make all R of I as infinity. And also, if I don't have Li comma Ri in my both map, I will make both of Li comma Ri as infinity, right? That's just because if an element is not in the map, by default C++ declares its map value as 0, right? And that's it. Now what I can do is I will calculate. I will also update the values of the map. So all L of I is minimum of its already minimum of the already what the value of all L of Li is, and C of I. Similarly, all R of I is minimum of all R of I and C of I. And similarly, both of Li comma Ri is minimum of both of Li comma Ri and C of I. And then if I have MNL and MXR as a part of my both map, then I will consider it as a candidate for my answer. So answer of I becomes both of MNL and MXR. And also the second candidate of my answer is all L of minimum L plus all R of maximum R, right? So that's it. That completes the solution. If I do this, I will just take the minimum of these two values, and that will be the answer to S is equals to I. And finally, I will just output the answer for all S from 1 to n. And yeah, this completes the solution to problem B. I'll admit this was kind of a trickier problem as compared to a normal B problem. But if you have enough knowledge of C++ STL and you have practiced enough problems, then it should have been an easy one for you, right? And if not, this is a good time to start doing problems relating to C++ STL, since it is a very useful tool in comparative programming in general, right? So yeah, this completes the solution to problem B. Let's move to the next problem now, problem C. This is an interactive problem and a very, very good problem. I found this problem to be really amazing. The solution is really not that difficult. So let's just see what this problem has to say. So the jury has a permutation P of length n, and it wants you to guess it. For this, the jury created another permutation Q of length n. Initially, Q is an identity permutation, that is Qi is equals to I for all I. And you can ask queries to get Qi for any I you want. So after each query, the jury will change Q in the following way, right? So if there was no change, then the problem becomes really easy. You can simply query for every I and get the permutation Q, but that doesn't make any sense because we need the permutation P, right? So let's see how the permutation Q is actually changing. So once we do any query, what happens is at first the jury will create a new permutation Q prime of length n, such that Q prime of I is equals to Q of P of I, and then the jury will replace the permutation Q with the permutation Q prime, right? That's exactly what's happening. So first I will create a permutation Q prime where Q prime of I will just be Q of P of I for all I, and then I will replace my permutation Q with the permutation Q prime. So I can ask no more than 2n queries and I have to guess the permutation P. That's the entire problem. A very short and crisp statement, but overall the problem is really beautiful. Okay, so I hope the problem statement is clear enough. It's an interactive problem. I can ask no more than 2n queries. I need to guess the value of the permutation P. In one query, I can get any index of the permutation Q. And once I make a query, the permutation Q is transformed into the permutation Q prime, where Q prime of I is Q of P of I. Right? So that's the problem. Let's see how we can solve this. So let's see what exactly is happening, and that is probably a good idea whenever you are trying out an interactive problem. See how your query is changing stuff and see what exactly is going on. So let's look at the initial situation. So initially I haven't done any query, and let's see how the permutation Q is looking like. So permutation Q looks something like this, right? So let's say n is just 10 or something like that. So initially this is how my permutation is looking like, right? Yeah. So what happens once I do a query? right? So once I do a query, what happens is that I create a new permutation q prime where q prime of I is equals to q of p of I, right? So uh, q prime of 1 becomes q of p of 1, right? And initially I know that q of I is equals to I, so q of p of 1 is just p of 1. Notice what I'm doing here. So then I get p of 1, and then q of 2 becomes q prime of 2 becomes q of p of 2, but I know q of I is just is equals to I because q is an identity permutation, so q of p of 2 is just p of 2. Similarly, q of p of 3 is p of 3, then p of 4, then p of 5, p of 6, p of 7, p8, p9 and p10, right? So that's what happens after my first query. And now what happens after my second query? So now q of 1, notice q of 1 becomes q of p of 1, right? So q of p of 1, but q of I is q of I right now is p of I, right? So q of p of 1 is p of 1, p of 1. Similarly, p of 2, p of 3, so on and so forth up till p of 10. So this from this point you begin to see the pattern, right? So initially I have 1 2 3 up till n, then I have p1 p2 p3 up till p10, then I have p of 1, p of 2, p of 3 up till p of 10, and you will notice if you keep doing this you will get p of 1, p of 2, p of 3 up till p of 10, right? So this is basically the structure of a query, and this is what is happening once you do a query. So 1 p is adding every time to every index. So this is what is going on. Okay, so once you've done this, now let's start making some observations. This was a pretty trivial part. I hope, and everyone who gave 10 to 15 minutes to this problem must have figured out this is what exactly is happening here. So now let's make a very general observation about permutations in general. And this is the most important observation, and this will come in handy in many other problems related to permutation that you will see in general on Codeforces or in competitive programming in general. So a very important fact about a permutation. So in a permutation P, if we add an edge between I and p of I for every I, then we get a graph consisting only of several simple cycles. So this is the most important observation in this problem and a very important property of a permutation as well. So what I'm saying here is that for every I, if I add an edge between I and p of I in the permutation, then I will get a graph which consists only of several simple cycles. So what that means is that I will get a graph which looks something like this. So it consists several connected components, and all of the connected components are just cycles. So this is what the permutation will look like. All of these vertices are nodes on the graph, right? So for any value of n, all the elements will get distributed as a part of a cycle. So this is what happens if I add an edge between I and p of I in a permutation. So every node becomes every index of the permutation becomes a part of a cycle, and every connected component is just one simple cycle. So yeah, this is the most important observation that we had to do in this problem, right? So from I we'll move to p of I and then to p of I. So let's say this is I. So let's say this is I. If this is I, then this will be p of I. This will be p of I. This will be p of I. This will be p of I, and so on and so forth, right? So this is what is happening in a this is what happens in a permutation. And so if from I we move to p of I, then we move to p of I, and we just keep doing that, then eventually we will come back to I. That is my claim. And yeah, so I will come back to I after exactly the number of steps which is the same as the size of the cycle. So if the size of the cycle is sz, then I will come back to I after exactly sz steps. So that's the main important observation in this problem, and that is also a very important property of permutations in general, right? So now with that in mind, let's look at this. Let's look at the structure of a query. So what's happening is, from 1 we are moving to p1, then we are moving to p of 1, then we are moving to p of 1, and notice that we are moving in a very similar fashion as described by me in this particular cycle, right? So what happens is that, so from 1 I am moving to p1, then I'm moving to p1, then I'm moving to p1, and so on and so forth. So I have a guarantee that after several moves I will get back to 1, right? Because I am beginning my cycle from 1, so after several moves I am bound to get back to 1, right? And that will mark the endpoint of my cycle. And so what that proves is that until and unless I am in that cycle, I am in this cycle and I am getting new and new elements, I will keep getting answers to several indices, right? So first of all, I will get the answer to p of 1. Then I will get the answer to p of 1. Then I will get the answer to p of 1, and so on and so forth until I encounter 1. And so I can just keep querying for the first element of the permutation, and I will keep getting answers to these unique indexes, right? So I will just keep getting answers to all these unique indices, like what is the element at this position for every position which is unique. And once I get back to 1, then that means I have marked the end of my cycle. And now if I query for index number 1 again, I will get the answer to a index which I already have an answer to, right? So now it doesn't make sense to keep querying for index number 1. So let's write down the solution. Start querying for index 1 and keep doing it unless you reach the end of the cycle containing index 1, and you will reach the end when you get back to 1. That's the only way you are reaching the end, because at each time you are going one step to the right, and you will get back to 1 eventually after some steps. And once you do that, that will mark the end of your cycle. And if you keep querying on index 1, you will keep going through the cycle again and again, and that will be a waste of queries, right? So once that happens, increase index to 2 and start querying from 2, right? If you already have the number which is present at 2 initially, then you don't need to do any single query at 2, just move to 3. Similarly, just keep increasing your index and keep querying on that index as long as you are getting new elements. And as soon as you start getting repeated elements, that means you have completed a cycle, so you can increase your index and just keep querying. So increase index to 2, keep querying until you get new values, and when you get a repeated value, increase index to 3. And basically you just have to keep doing this, and eventually you will get all the n values of the permutation, and you will have the complete answer ready with you, right? So basically this is the entire solution to the problem. Start querying at index 1, keep querying as long as you are getting new values, and then increment your index and keep querying, right? So yeah, that's basically it. And for every index, just do one query and check if you are getting a new element. If you are getting a new element, then that means that particular index is a part of another cycle. So you query for that index again and again as long as you finish the cycle. And when you have finished the cycle, you increment your index and check whether the incremented index is a part of a previously computed cycle or a new cycle. So if it is a part of a previously computed cycle, you just have to make one query and figure out that, oh, I've already completed this cycle, so now this index is useless to me, and increment your index, right? So yeah, That's the entire solution. I know it's a bit tricky to understand, but if you have some basic knowledge about permutations and the way a permutation can be converted into a graph containing a collection of several simple cycles, then it's not very hard to see what's going on here. Right. So let's see what's going on. Let's have a look at the code for better clarity. So first of all, I do a query from index 1 just so that I convert this index. I convert q to p1, p2 up till p10, right? And so my index is 1 and the current element which I will get is also 1. And so I do a while loop while found is less than n, and found is the total number of elements that I have found until now. So that's the total number of indices whose value I have found. And if found becomes n, then I'll just break out of this while loop. Now, current answer is query of index, right? So initially my index is 1 and current answer will be query of index, right? And also current is that index whose answer I am getting, right? So answer of cur is going to be cur answer and found will be incremented, right? And now I will check if answer of cur answer is equal to -1 or not. So if answer of cur answer is equal to -1, that means I haven't reached the end of the cycle. So I will just do cur is equals to cur answer and I will keep going. Otherwise, if answer of cur answer is not equals to -1, that means I have reached the end of the cycle. So then I will figure out the next index, which is a part of a new cycle. So I will loop from index plus 1 to n and I will query for I and I will check if answer of q is -1. So if answer of q is -1, then that means I am beginning a new cycle. And if answer of q is not -1, then that just means that the index I is a part of a cycle which I have previously computed, right? But if answer of q is -1, then I have reached an index which is a part of a new cycle. And so I will do idx equals to I, cur is equals to q, and then I will continue in my while loop, right? So yeah, that's all that is happening. And once I come out of the while loop, I'll be sure that found has become n. And so I have found out every distinct location. And then I will iterate from 1 to n and output all the values of the found permutation, right? So yeah, this basically completes the solution to problem C. It was a pretty interesting one for sure. So yeah, now let's move to the last problem that we'll be discussing today, problem D. And before I start with the solution, I would just like to say that this was a troll problem. Like, there is a very involved problem statement, but once you get to the solution is really simple. And once you actually understand the solution, you might argue that why is this problem not problem A or problem B? That's why I'm saying this is a troll problem, right? Okay. So the problem statement is big. Let me explain in brief what the problem is saying. So essentially we have a 2n cross 2n grid and I have n square friends, right? And initially all the n square friends are in the top left corner of the grid. By top left corner, I mean the n cross n grid, which is in the top left corner, right? So I have n square friends. There is one friend in one cell in all the cells in the top left corner of n cross n size. So if n is equals to 2, then I can say that there are 4 friends in these 4 cells, 1, 1, 1, 2, 2, 1 and 2, 2, right? And my goal is to move all these friends from the top left corner to the bottom right corner. Bottom right corner is just the n cross n grid towards the bottom right of this 2n cross 2n grid, right? All of this grid can be divided into 4 parts: top left, top right, bottom left, bottom right, right? And I have n square friends in the top left grid, and my goal is to move all of these n square friends to the bottom right grid. And I can do that by performing some operations. So essentially I have 4 types of operations, and the first type of I have 2 types of operations on a row and 2 types of operations on a column. The operations are simple. Basically what I can do is I can select a row and I can do a right shift operation. So I will move every element to the right, and obviously the element which is at 2n position will go to the first position, right? And similarly I can choose a row and do a left shift operation. So every element in that row every friend in that row will be shifted to the left by 1, and if there is a friend on column number 1, then it will be shifted to column number 2n. And similarly I have 2 operations for every column. I can select a column and do a upshift operation and a downshift operation. In an upshift operation, the element which is at row number 1 will move to row number 2n. Similarly, in a downshift operation, any element which is at row number 2n will move to row number 1, right? So in simple terms, these are the 4 operations that I have. And my goal is to move every friend from the top left grid to the bottom right grid, right? And I can do that using some operations for sure. But the twist in the question is that in every cell there is snow, and I have to like, if I am moving a friend to a cell, then that cell cannot have snow, right? Because if that cell has snow, then the friend will get sick. Then the friend will get sick, right? So my goal is to move friends from the top left grid to the bottom right grid, making sure that if I'm using a cell, that is, if I am having a friend at any cell, then that cell is snow free. And to make a cell snow free, there is a cost, and for each cell I have been provided with that cost, right? Cxy. So for each cell it requires Cxy coins to remove all the snow from the cell x comma y. And before I start doing any operations, I have the choice to select a few cells and remove the snow from them. And once I start doing operations, I can't remove snow. So I have to decide which cells to remove snow from the beginning. And once I have decided that, I can move my friends only to those particular cells which do not have snow, right? And doing that, I need to move from the top left grid to the bottom right grid. Also, they have made sure that there is no cell in the top left grid which has snow, because in that case a friend will already be in a cell which has snow and he will already get sick. So I will lose, right? So yeah, for all the other cells, there is a valid non-negative cost to remove snow from that cell, and I need to choose some cells, remove snow from them, and then I need to move my friends only through those cells which don't have snow in them to the bottom right corner. Also, the bottom right corner cells might have snow in them themselves, and so it makes sense to remove snow from every cell in the bottom right corner, because eventually, finally, every friend has to settle in the bottom right corner. So yeah, that's the problem. Obviously, I need to find out the minimum number of coins that I will need so that I can successfully move my friends from the top left grid to the bottom right grid. So that's the problem statement. I hope it's clear enough, and let's see how we can solve this problem now. So according to the problem statement, we need to choose some cells and remove snow from them. Then move all friends from the top left grid to the bottom right grid, such that no friend is ever on a cell which has snow. That's the problem. So the first observation. So this is a pretty simple one. So the final state of the matrix is going to look like this. All the friends will be on the n cross n grid, and will be on the n cross n grid which is at the bottom right position. And so it makes sense that no cell in the bottom right grid should have snow, right? So we have to choose every cell in the bottom right grid. So answer will be initially the answer will be the sum of the Cij values of all ij such that the cell I comma j belongs to the bottom right grid. And that's a very obvious thing, because finally all of the cells in the bottom right grid will be occupied, and so they can't have any snow. So with that sorted, now let's come to see what we can do for the rest of the cells, right? So yeah, it will be better if I just take in a diagram and try to explain from that, using like an 8 cross 8 grid or something like that. Yeah, I think this looks good. Okay, great. So I have a grid like this, right? So this is an 8 cross 8 grid. So let's say n is equals to 4 right now. See, cool. So in the beginning, I have n square friends in the top left grid, right? So I have friends here. And my goal is to move these friends in the top left grid to the bottom right grid, and the order doesn't matter. I just need to make sure that every friend which is here is now here, and that's it. I don't need to maintain any kind of order, and I just need to make sure that every friend which is in the top left grid is in the bottom right grid, and no two friends are in the same cell. That's also another thing. Okay. All right. I've already proved that I need to add the costs of every cell in the bottom right grid, because eventually that cell is going to be occupied and it can't have any snow, right? And now let's make the very important observation. So what I'm going to do is that I'm going to focus on the corner friends. By corner friends, I mean these particular friends. So a friend who is in this corner, who is in this corner, a friend who is in this corner, and in this corner. So I will focus on these 4 friends for now. Okay. So let's look at the first operation which moves any of these 4 cells. So we will look at the first operation which moves any of these 4 cells. And by that I mean that initially I know that all these 4 cells are unmoved right now, and I'm looking at the first operation which is moving any of these 4 cells. So it is guaranteed that these 4 cells are not moved right now. They are at their initial positions only, and I'm looking at the first operation which changes the position of any one of these 4 cells, right? So yeah, how can we do that? We can do that in total 8 ways. And the way we can do that is we can either choose the first row and perform any of the 2 types of operations available to me. So if I perform those operations, I will move this particular cell and I will also move this particular cell, right? Also, I can choose the last row and perform any of the 2 types of operations that I have available. Similarly, I can choose the last column, that is column number n, and perform any of the 2 types of operations that I have for column number n. And similarly, I can choose the first column and perform any of the 2 types of operations, right? So in total, I have 8 types of operations which are moving elements in the corners, right? So let's look at all these operations order wise. So if I choose this first row and perform the right shift operation, then what happens is that the element which is here comes here, and this gets disappeared, right? So if I do a right shift operation, this is happening, right? So this particular cell is getting occupied, right? Okay. But if I do a left shift operation, what is happening is that this particular cell is getting disappeared, and this particular left cell is coming here, and all the other positions are unchanged, right? So this is what happens when I do a right shift operation, and this is what happens when I do a left shift operation, right? Okay, great. Now, so you can notice that this cell is getting occupied and this cell is getting occupied. So either this cell is getting occupied or this cell is getting occupied. Okay, so this is what is happening if I'm choosing the first row and doing either the right shift operation or the left shift operation, right? Okay, great. Now let's choose the last row. So I'm choosing the last row and I'm doing the right shift and left shift operation. So you will notice that either this cell is getting occupied or this cell is getting occupied, right? It is a completely analogous situation to choosing the first row. Okay, and now if I choose the first column and I do a downshift operation, then this cell will be occupied, and if I do an upshift operation, then this cell will be occupied. Pretty obvious. Similarly, if I choose the nth column and I do a downshift operation, then this cell will be occupied, and if I do an upshift operation, then this cell will be occupied, right? And so what I notice is that at least one of these 8 cells will be occupied. So at least one of these 8 cells will be occupied. Right? Notice that I'm looking at that operation, which is the first operation in which any one of these 4 corner cells is getting moved. So any one of these 4 corner cells will be moved, that is for sure. And in that operation, at least one of these 8 cells will have to be snow free, right? Because at least one of these 8 cells will be occupied. And so for the cell to be occupied, it has to be snow free. So the first observation we have to make at least one of these 8 cells snow free, and that is obvious because these corner cells will be moved once, right? And once they are moved, the first operation which moves any one of these corner cells will make at least one of these 8 cells occupied, and so at least one of these 8 cells has to be snow free. Great. So with all this done, now let's make a very crucial claim which will basically just solve the problem. So claim. So my claim is that it is enough to clear just one out of these 8 cells, and then all the friends will be able to reach the bottom right corner. So this is my claim, and let's see how we can prove this claim, right? So what I will do is I will choose one of these 8 cells and I will show that it is enough to clear that one cell, and all of these other cells are just symmetrical, right? Because there is no difference between these 8 cells. If I can go to from the top left to the bottom right corner using just one of these 8 cells, then I can do that using all of these 8 cells, right? Because it is totally symmetrical. So I will choose this particular cell, this cell, and I will prove that it is possible. If I just clear this cell, I can move every friend from the top left corner to the bottom right corner. That's the claim, right? Okay, so let's see how we can do this. So I will just illustrate the process of doing it, and that will just complete the proof. So the first operation that I'm going to do is I'm going to choose column number n and do a downshift operation, and what that will do is that will make my situation as something like this, right? And then I will choose row number n plus 1 and do a right shift operation. So essentially what happens is that I move this friend here. So now I will again choose the nth row and nth column and do a downshift operation, right? And then what happens is something like this. And then I will again choose the n plus 1th row and do a right shift operation. And so what happens is that everything gets shifted to the right, and then I will just keep repeating this process again and again. And so I will again do a downshift operation on column number n, and I will get a situation like this. Then I will do a right shift operation on row number n plus 1, and I will get something like this. Then another downshift operation on column number n, so I will get something like this, and another right shift operation on row number n plus 1. And so I will get something like this, right? So I noticed that using these operations, I have moved the nth column and converted it as a part of the first row in my bottom right grid, right? And now what I will do is I will choose this n plus 1th row and I will do a downshift operation. And so what happens is that each of these 4 cells, each of these 4 friends will be shifted to down. Will be shifted by one column will be shifted by one row to the bottom, right? And so what happens is that everything gets moved from here and it comes here. So now what happens is that what I can do now is that I can now choose my column is equals to 3 and I can do a right shift operation, and then what will happen is something like this. Everything will be shifted to the right, and now this situation is completely analogous to the previous situation. I can move this entire nth row and convert it to the first. I can move this entire nth column and convert it as the first row in my bottom right grid. So eventually I will be left with something like this. Now again, I can choose row number n plus 2 and do a bottom operation, and then I will choose row number n plus 1 and do a bottom shift operation, and then again the topmost row will be clear of my bottom right grid, right? And I will have something like this. Right? And then I can choose column is equals to 2 and do 2 right shift operations. So I will do 2 right shift operations here on this column, and again now I have my nth column with me, right? So again I can convert this nth column as the first row in my bottom right grid, and I will do that. And I will be left with something like this. And so again I will choose all of these 3 rows one by one and do a bottom shift operation, and then again the first row will be clear. So I will be left with something like this. And yet again I can choose column is equals to 1, and then I can do 3 right shift operations on it and convert it as my nth column in the top left grid, and I will be left with something like this. And then I can again choose this nth column and convert it as a part of my first row in the bottom right grid. So I will be left with this. And voila, I have moved every friend from the top left grid to the bottom right grid using just one cell, which is this one. I have just used this cell, right? And this is one of the 8 cells, and rest all the other situations are analogous. I can make certain constructions. I can make some constructive algorithm and move all the friends in the top left grid to the bottom right grid using one of these 8 cells, right? So that proves the claim that it is enough to just clear one of these 8 cells. And so it is enough to clear one of these 8 cells, and also according to the previous claim, it is essential to take at least one of these 8 cells. And so what that means is that we have to take exactly one of these 8 cells, and we will just take that cell which has the minimum value of cost, right? And that's it. That is the entire solution, and that's why I was saying that this is a troll problem. You don't have to do anything special here. Just add all the Cij values in the bottom right grid and take the minimum of the Cij values of all of these 8 cells, and that's your answer. So yeah, let's just have a look at the code. Very, very small and crisp code. You create a vector, take in the cost values. If they belong to the bottom right grid, you straight away add them to your answer. And then these are the 8 cells. You can just add these 8 cells into a vector, sort that vector, and take the first element in the sorted vector and add it to our answer, right? So this is it. This completes the solution to problem D. And yeah, these are all the problems that I had to discuss today. So that's it for today. Thank you so much for watching till the end, and I will see you in the next video.